We at Convair Astronautics are often asked to outline the development history of the Atlas intercontinental ballistic missile. This is a film of the presentation we give. The Atlas is this nation's first ICBM. Its development is a tribute to the achievement of American scientific, industrial, and military groups. Its history goes back to the months following World War II, when Convair was given a contract to study the development of a rocket-powered missile which would deliver a nuclear weapon to a range in excess of 5,000 miles. As this chart shows, we began work on the first ICBM development program in 1946. This was Project MX-774. The Defense Department terminated the project in 1947 for economy reasons, but we were allowed to finish and launch 3 test vehicles in 1948. Convair designers introduced several new techniques in missile technology, including steering of the missiles by swiveling the rocket engines, use of integral fuel tanks, and separation of the nose cones, to mention 3 that are in universal use today. The launchings at White Sands successfully demonstrated these principles. Following termination of the MX-774 program, Convair kept some of its key people together as a team to continue studying ballistic missile technology. In 1951, Air Force support was renewed under the MX-1593 contract. At first, a study program to compare the ballistic and glide approaches. Convair recommended concentration on the ballistic missile in September, and the program, now called Atlas for the first time, was broadened to include component development. Meanwhile, Convair had proposed an Atlas crash program in the summer of 1953 in a report to the Assistant Secretary of the Air Force for Research and Development, Trevor Gardner. That fall, he appointed the Strategic Missiles Evaluation Committee, headed by Dr. Van Norman, to survey the long-range missile programs. The committee concurred in our plans for a stepwise development, using only components designed to the ultimate missile configuration. The 1953 Atlas design was essentially the present ICBM, but was 1/3 longer, 2 feet greater in diameter, and powered with 5 engines to carry the large, heavy warhead of that time. Early in 1954, the committee recommended acceleration and broadening of the Atlas effort, and that spring the Air Force gave the ballistic missile top priority. What is now the Ballistic Missile Division was set up that summer with General Schriever in command, and the Air Force contracted with Ramo Wooldridge for systems engineering and technical direction. In the fall of 1954, confirmation of warhead weights and yields was received from the Atomic Energy Commission, and a complete review of all possible ICBM configurations was conducted. As a result, Atlas was scaled down to the present 3-engine configuration. A full-scale tank was completed in October 1954. This was used for structural and dynamic tests, which proved completely that a thin-walled, pressurized monocoque tank is feasible for ballistic missiles. This gives us the lightest structure and hence the most favorable mass ratio yet devised for these kinds of weapons. Convair received contractual go-ahead in January 1955. Since that time, all members of the Air Force industry team have been working as hard as they could to develop the weapon system. The first Atlases were fabricated at Convair San Diego in Building 4, the long structure outlined in this photograph. More than 6,000 B-24s were assembled here during World War II. Here is the Atlas assembly line in Building 4 in 1956, the year the first Atlases were delivered to the Air Force. At the Point Loma test site, which looked like this in 1956, we were accomplishing structural and flow testing, validation of ground support equipment, and testing of launchers and booster separation. At Sycamore Canyon, near San Diego, facilities were built for captive testing entire missiles. The picture shows the first engine ignition in December of '56. Similar testing was conducted in stands built at the Air Force's Missile Static Test Site, Edwards Air Force Base, California. In 1955, General Dynamics had decided to invest $20 million in a new plant to be devoted entirely to the Atlas and development of space technology. Construction was started in 1956 on a 250-acre site in the outskirts of San Diego. The first Atlas flight test took place in June 1957, only 6 weeks behind the original schedule established in January 1955. Missile 4A made a smooth takeoff from Complex 14 at Cape Canaveral, rising straight as a string, but failure occurred as a result of excessive heating in the engine compartment. A similar failure in September enabled Convair and Air Force engineers to determine fixes, and Missile 12A was launched beautifully on December 17, 1957, achieving all of its test objectives. This was the free world's first successful intercontinental ballistic missile flight. Just a year and a day later, Atlas had progressed so far that it was able to boost itself into a satellite orbit. Today, the Atlas is being fabricated in the new astronautics facility at San Diego. Additional construction since the plant was finished in 1958 has brought the General Dynamics investment to about $25 million, and the Air Force has installed more than $15 million worth of heavy machinery and other equipment. I would like to show you a few of the activities which go on here to give you some impression of the many kinds of people and equipment needed to develop and build an ICBM. Here, for example, is one of the world's largest integrated computing facilities. Digital and analog equipment with interconnect capability, located adjacent to data reduction equipment, fills more than 30,000 square feet of floor space in the engineering laboratories. In a complete environmental test laboratory, we can subject components to extremes of cold and heat to determine whether they will be able to stand the conditions of missile service life and operation. Electronic complexity is an important characteristic of ICBMs. This is one corner of the electronic assembly area. This is the high bay end of the factory, where facilities and tools are arranged for the unique fabrication methods used in building Atlas. As you know, Atlas tanks are constructed of thin, tough sheets of stainless steel. There are no stringers or stiffeners to maintain shape. This is done by pressurizing the tanks, the same way a football maintains its shape through internal pressurization. The steel comes from the mill on large spools. It is pulled out on a table and cut to length. Then the ends of the band are welded together to form a ring. These 10-foot rings are the basic building blocks of the Atlas airframe. The clips and brackets needed as attachment points for equipment pods and the like are welded to the rings. Then the rings are joined together by welding in the major assembly fixtures. Tooling rings are used to maintain cylindrical form while the tank is under construction. In this photo, the light patterns show that the tank has not been pressurized yet and hence is slightly wrinkled. The tank becomes smooth and drum tight when pressurized for handling. Less than 10 pounds per square inch is required. A suspension point at either end is all that is needed for handling the tanks by overhead cranes. After leak testing, the tanks go to the elevated final assembly docks. A one-station final assembly technique is used. Here, workmen are installing electronic and mechanical equipment in one of the external pod areas. From its final assembly station, the completed missile is moved to a checkout station and hooked up to consoles beneath the dock. Here, a complete composite test is run to verify the compatibility of all missile systems. Then the missile is lowered into the yellow handling trailer and hauled away to the appropriate test site or operational base. Some deliveries are made by airlift in a modified C-133 that picks up the entire missile in its handling trailer. In operation, all the Atlas engines are started on the launcher, and the missile is held down in order to be sure that the engines are operating properly. After this is determined, the launcher releases the missile, and Atlas takes off vertically, propelled by rocket engines made by the Rocketdyne Division of North American Aviation. It continues to go upward vertically for about 10 or 12 seconds, during which time the missile rolls about its vertical axis in order to establish the target azimuth plane. The missile programmer then commands a zero gravity turn in the direction of the target. The missile continues in first stage operation under control of the missile autopilot. After about 2.5 minutes, the guidance system commands the booster engines to shut down, and these engines, together with the booster section, are jettisoned and fall away. The Atlas then continues under the operation of its sustainer engine and the two small vernier engines, which provide roll control during second stage of the flight. The missile is guided during second stage by the ground radio guidance system furnished by the General Electric Company. After about another 2.5 minutes, the sustainer engine is shut down, and the vernier engines are used to make a final velocity adjustment for the missile. Then, the reentry vehicle is unlatched. Small solid propellant rockets in the main Atlas tank move the tank away from the reentry vehicle, and it continues on its way to the target without further guidance. It takes about 30 minutes for the reentry vehicle to reach the target after launching. Atlas reached the milestone of initial operational capability in the fall of 1959, when Complex 576-1 at Vandenberg Air Force Base, California, was turned over to the Strategic Air Command. On September 9th, a crew from the 576 Squadron launched Atlas 12D from this complex. This was a completely successful shot. Thus, Atlas has reached the transitional stage of initial operational capability, while development work continues. At this point, the weapon has demonstrated completely its ability to perform even better than the original design objectives called for. Because it is the most powerful booster in the free world, Atlas has been chosen as first stage for many military and civilian space programs. Here is Atlas 10B, the talking satellite, as it appeared after being launched into orbit on December 18, 1958. 10B carried the heaviest payload of any American satellite launched during the International Geophysical Year. This was 122 pounds of communications relay equipment used to broadcast President Eisenhower's Christmas message from space and for communication experiments between satellite and Earth. 10B remained in orbit for some 33 days. Our Series D missile is the booster for a number of spacecraft, the first being the Mercury capsule that will carry the first United States astronauts into orbit. Atlas Able uses second and third stages adapted from the Vanguard project and can put moderate payloads into the vicinity of the Moon. Atlas Agena is the current name for the two-stage vehicles employed in several military projects that used to be covered by the title WS107A. A liquid propellant stage built by Lockheed Aircraft rides on top of the Atlas. Centaur combines a modified Atlas with a second stage, which is also built in the Atlas factory. It will give the United States its first capability for putting up payloads roughly equivalent to those of the Russian Lunik series. Atlas has progressed at a more than satisfactory rate in the research and development program, but we still have a big job to do. In the months to follow, construction and activation of operational bases is a challenge as tough as development of the weapon system these bases will support. A maximum effort is now underway to meet our most important objective, to get the Atlas into our national arsenal, into the operating force of the Strategic Air Command.